Hi, this is the first lesson of thermodynamics. So here we go. We've finished all the A-level stuff, so this is something that, as we talked about last week, it's probably going to be useful for at least 4 of the 5 of you, probably be useful for all 5 at some point. And hey, learning is fun. So today, just a nice easy video to ease you into the warm bath that is thermodynamics. So what I'm going to do is just basically explain what it is and also try and get across the idea of entropy, which is a really important but slightly slippery concept that we're going to need. So, what is thermodynamics? We just don't know. It's the study of stuff heating up, cooling down, and fluids, which in physics means a liquid or a gas, we call both of them fluids, how they move. So sort of fluid dynamics and stuff is also part of thermodynamics. It's just about how sort of engines heat up and cool down, gases expand, aerosols, that kind of malarkey all follows under thermodynamics. It was invented by Einstein. He invented an entire branch of physics. We're always very impressed that he did special relativity and all that jazz, but actually he also kind of just invented thermodynamics on the side. In the same year he invented special relativity. It's a pretty good year, pretty good year. And he had this really clever idea, because people have been trying to understand thermodynamics for a while. They've been trying to get the equations to work, trying to model these things, and no one ever been able to really do it. Well, Einstein, his genius was, he said, well, let's get rid of time. Time doesn't exist in thermodynamics, which is weird, because we think of all of physics as stuff changing with time. But what Einstein realised was that thermodynamics, you kind of just ignore the time bit and instead just have stuff happen. And a lot of it's solid state. So if you imagine just like water gushing around a pipe, you just imagine it at any moment and assume that it's doing the same thing on any given second, even though each individual bit of water is moving. And the heating up, cooling down part, he said, don't worry about how long it takes. We can find that out in other ways. If we're interested in just how it's heating up and cooling down, let's just look at all the other stuff that isn't time, and that'll actually tell us more. Because so often what you're looking at in thermodynamics is, if I take this box of air and I make it bigger, what will that do to the pressure inside? What will that do to the temperature inside? If I take an aerosol and I squirt it so the gas that's very compact inside suddenly spreads out, what will that do to the temperature of that gas? None of these are questions which are time dependent. All they are just changing pressure, volume, amount of gas, temperature, and as you fiddle with some, the others also change. But notice the word time doesn't appear in any of that. There is a problem with this, which is time does something that's so fundamental we forget it's there. Time tells us in which order things happen in. A to B to C to D. Stuff falls. Masses come together. You know? So the question is, how do we have a direction for thermodynamics? How do we know which way things go? The answer is an idea called entropy. Entropy is basically how room temperature is the stuff. And more room temperature equals more entropy. Let me explain. If I'm in a room and I've got an ice cube and a hot cup of tea, the ice cube will warm up to the same temperature as the room. The hot cup of tea will cool down. They'll both become more room temperature. And this is what we call an increase in entropy. Entropy decreases when you've got hot things and cold things. It increases when everything becomes room temperature. It turns out that entropy always increases. So everything in the universe is slowly all getting the same temperature as each other. This is just something which is happening all the time. You might say, aha, but I can turn on the kettle and I can make the water hot and decrease entropy in the room. But what you'll find is that in order to create the energy that went into the kettle, you had to increase entropy, say at the power plant, in order to slightly decrease entropy in your kitchen, but overall in the universe, entropy will increase. Entropy will always increase. It turns out that's one of the very fundamental laws of the universe. And this actually gives you a direction of time for thermodynamics. If you're saying, well, will this heat up or cool down, will it expand, contract, what have you, you just go, well, which way will increase entropy? And that will tell you what order things will happen, which direction things will flow in, which way round the experiment will happen. This interesting means that you can just run everything backwards and the math still works fine. It's just we don't live in that universe. We live in the universe where the entropy always goes forward. And this leads to a rather interesting discovery, which is that if everything in the universe is becoming more and more room temperature, eventually, if you follow that thought far enough, at a certain point, everything in the universe will be the same temperature. Because all the hot things will have given all their energy to all the cold things, and all the cold things will heat up, till eventually everything is the same temperature. Now, for reasons that we will get to, it turns out that when everything is the same temperature, nothing can happen. And we call this the heat death of the universe. And that's where we're headed. On a long enough timescale, billions and billions of years from now, everything in the universe will be about 4 Kelvin, and at that point, nothing will happen. Everything will just stop. And I like that idea. Something to look forward to, I feel. Right, there's a question about entropy underneath. I'll see you tomorrow.